I mentioned in the last lecture that moment of inertia is a tensor quantity. That means it's like a vector, but instead of just having an x, y, and z component, it has xx, xy, xz, yx, yy, yz, zx, zy, zz components. But we only really talked about the diagonal terms, the xx and the yy. Today we're going to be talking about off-diagonal terms. So the way we calculated the off-diagonal terms is what you might imagine from the diagonal terms. Ixy is equal to the integral of xy dA. Now, having this integral, one thing that means is that we're no longer dealing solely with an axis in the x direction or an axis in the y direction. We are dealing with both. So we are finding the moment of inertia up about a point. And so x and y need to be both relative to that point. Now, physically, from an engineering standpoint, moment of inertia governs a lot of things about structure. Most notably, it governs failure. When will a beam fail under, in particular, compressive loads? It will also determine how does a beam fail when shear is applied. So, for example, the XX component of moment of inertia basically presents how strong it is to shear load in the x direction. So what the xy component of moment of inertia basically will deflect your shear. Now that sounds like a good thing, it's not. Basically, if you have a beam with a significant xy component and you apply a large load in the x direction, it will start to bend in the y direction. Typically not something you want to happen in your structural beams. Now, sometimes it can't be avoided. Sometimes you will have to have moment like that. But avoid it if you can. Now, these off-diagonal term for moment of inertia also has a parallel axis theorem about it. So the minimum moment of inertia in the xy component occurs when the point you're integrating about is the centroid of the area. If you're off of the centroid, then you would use this formula. Now notice if you're just shifted in the x direction, then your moment of inertia is still the moment of inertia of the centroid. Same if you're just shifted in the y direction. You have to have shift in both x and y in order to get this parallel axis theorem to do anything. Another thing to note, because this is not x squared or y squared, it is x times y, it is entirely possible for this to be negative, depending on which quadrant your specific chunk of area is in. Now, here comes some fun bit of math. This is section 10.6 on page 552. I strongly recommend opening up your textbook because there are a lot of formulas in here that I'm not going to write out, but I am going to talk about. So with a vector, you can describe the same vector in multiple different ways if you have different coordinate systems, different how you define what x and y are. Same thing with tensor. Now with the tensors, it's nowhere near as simple. Look at basically page 552, and you can see why. That is a bunch of math. Fortunately, you do not need to derive that. When you're doing a problem about changing the axes of the moment of inertia, use the equations in 10.9, and that's it. But one interesting result of the equation 10.9, particularly look at that last one, UV being the tilted coordinate system that the textbook uses. It is possible for IUV to be 0. No matter what IX and IY are, it is possible to find an angle so that IUV is 0. Now, as I was saying earlier, we don't like, or all else being equal, we would prefer to not have off-diagonal components. So this is a way to do that. Now, if you've ever heard the term eigenvector, that's what I'm going to be talking about. But I'm going to pretend you've never heard of eigenvector when I explain it, so it may sound weird. But basically, yes, we are doing this. We can find the eigenvectors. That is the direction that you can apply a force to the beam, and it will deflect in that direction. So, for example, if the IXY component of the beam is 0, then x and y are the eigenvectors. Uh, but if IXY is not 0, then we would have some other vectors. Now, you could try to solve the bottom equation 10(9) and set IUV equal to 0, but the text already does that for you. That is equation 10(10). So equation 10(10), the tangent of 2 theta p is equal to negative IXY over IX minus IY divided by 2. That will tell you how much you need to rotate your coordinate systems in order for your coordinates to be the eigenvectors. When you with that coordinate system, you will not have any diagonal or off-diagonal components. Now that's a lot of math. Fortunately, there is this really neat trick called a Moore circle that we can use to visualize all this. So the Moore circle is on page 555, so go ahead and look now. Basically, no matter what axis you use, these two coordinates, so think of IUU as the x-coordinate, IUV as the y-coordinate on a graph, not the actual real coordinates, but the coordinates on a graph. So, and this could be IXX and IYY if you want. But basically, these 2 points will form opposite sides of a circle. So looking at figure 1019b, the point A listed, that is at IXX comma IXY. And if it doesn't list this next point, but if you basically go through the center and then where that line would intersect at the other side, that would be IY comma negative IXY. So solving things like this, we can just use geometry to figure out. Now, I say just use geometry, we will end up doing the same math as from equation 10(10) and 10(11), but it is often much easier to visualize.